These are the answers to the AP Chemistry packet on topics 6.1 to 6.5. This is MCQ Practice, which means these are multiple choice questions for you to practice so you can prepare for the AP Chemistry exam. In the video description area, there is a link to the packet that accompanies this video. Now, let's take a look at our first multiple choice question. In question 1, it says, a student initiates a chemical reaction by combining two different solutions initially at 20 degrees Celsius in an insulated calorimeter. The temperature of the reaction mixture is monitored as shown in the graph above. Which of the following correctly classifies the energy change that occurs in this reaction and describes the flow of thermal energy between the reacting species, the system, and the surroundings? So this question falls under topic 6.1, endothermic and exothermic processes. And on this slide, you can see that one of the essential knowledge statements is highlighted. It says, when a chemical reaction occurs, the energy of the system either decreases for an exothermic reaction, increases for an endothermic reaction, or remains the same. For exothermic reactions, the energy lost by the reacting species, the system, is gained by the surroundings as heat transfer from or work done by the system. Likewise, for endothermic reactions, the system gains energy from the surroundings by heat transfer to or work done on the system. On this next slide, you can see something that I had presented in my video for topics 6.1 to 6.5. And at the top, you can see highlighted that note that the thermometer is usually considered to be part of the surroundings and not the system when we are monitoring temperature changes and heat flow during the process of either solution formation, such as dissolving a solid in water, or during a chemical reaction that takes place in an aqueous environment. So on the far left, the column says, how does the temperature change during the process? As we can see in the graph and the diagram for this question, the temperature increases during this chemical reaction. So when that happens, we say that heat flows from the system, the reacting species, into the surroundings, which could be the water molecules in the aqueous solution. Again, thermometer is considered part of the surroundings, so we have an exothermic process in which heat is flowing from the system into the surroundings. For example, this is an exothermic process. It's an instant hot pack, and once you squeeze the bag to initiate a chemical reaction, then heat flows from the system, which is the reacting species inside that pouch, to the surroundings. The temperature of the surroundings increases and the hot pack feels hot. That's an exothermic process. So back to this question and the diagram, the initial temperature of the solutions before they were combined was 20 degrees Celsius, and we can see that over time the temperature increases. So now that we know that the solution temperature increases as the reaction proceeds, we can conclude that this chemical reaction is classified as exothermic. Here are the four choices. If it's an exothermic reaction, we can go ahead and eliminate choices A and C because they say it's endothermic. And now with respect to the flow of thermal energy, let's take a look at that essential knowledge statement for topic 6.1. For exothermic reactions, the energy lost by the reacting species or the system is gained by the surroundings as heat transfer. So the correct answer to question 1 is choice B. It's an exothermic reaction, and thermal energy lost by the reacting species or the system is gained by the surroundings. Now let's take a look at question 2. In question 2, it says a student dissolves a sample of solid potassium iodide, Ki, into a sample of water in a coffee cup calorimeter. The solid dissolves completely, and the student monitors the temperature of the solution, observing that the temperature decreases from 21 degrees Celsius to 18 degrees Celsius. Which of the following best helps to explain the energy change that occurred during the dissolution of solid potassium iodide? So unlike question 1, in which the temperature increased when the two solutions were combined to form a chemical reaction, here we can see that the temperature actually decreases during the formation of a solution of potassium iodide. So it's not an exothermic process, as we saw in question 1. It's going to be an endothermic process. Again, the thermometer is usually considered to be part of the surroundings and not the system. And so whether it's a chemical reaction that takes place in a calorimeter or simply dissolving a solid in water to form a solution, if the temperature decreases during the process, then heat flows from the surroundings, which would be the water molecules present in the solution, into the system. And the system can be defined as the particle level events that are taking place during the dissolution of that solid. So we have an endothermic process. So it's not going to be a hot pack as the example which I used in question 1. It's going to be an instant cold pack. So during the process of an instant cold pack, whatever's happening inside that pouch, heat is flowing from the surroundings to the system, and the temperature of the surroundings decreases and it feels cold. So we know that the solution temperature decreases during the dissolution of solid potassium iodide. Therefore, we can conclude that this process of solution formation should be classified as endothermic. Now, let's see which of the 4 choices we can eliminate at this point. In choice A, it says that when solid potassium iodide dissolves in water, ions of aqueous potassium ions and aqueous iodide ions are formed. And although that is true, that definitely takes place, there's no mention of any attractive forces that are being broken or formed, so it's hard to say that choice A is the best explanation of the energy change that occurred. It is a true statement of what happens when an ionic solute dissolves in water, but there's no indication of energy changes or attractive forces being broken or formed. Now, choice B is actually incorrect because potassium iodide is an ionic substance. It contains a metal and a nonmetal, and so when it dissolves in water, it forms ions. It does not form molecules of potassium iodide. So the correct answer to question 2 is either choice C or D. Choice C is talking about strong attractive forces between potassium ions and iodide ions, and choice D is talking about strong attractive forces between potassium ions and water molecules. Now we should consider whether these attractive forces are broken or formed and how that relates to the energy. So breaking attractive forces between particles does require energy. So that is an endothermic process in which energy is absorbed. On the other hand, forming attractive forces between particles is going to release energy. That's an exothermic process. Now, on this next slide, this is something that I had presented in my packet for topics 6.1 to 6.5. And what this diagram does is it breaks down different steps in the process of dissolving an ionic solid into water. So step 1, attractive forces between the ions in the solute are broken. Again, breaking attractive forces would be an endothermic process. Step 2, attractive forces are broken between some of the polar solvent molecules. Again, breaking attractive forces would be an endothermic process. But then in step 3, attractive forces are formed between the ions and the polar molecules. That would be ion dipole forces. And so because they are formed, that would release energy. So that's exothermic. Now we already know that the dissolution of solid potassium iodide into water happens to be an endothermic process because the temperature decreases during this process. So we're looking for the correct answer, which would involve something that's endothermic. In choice C, it's talking about strong attractions between the ions of potassium and iodide in the crystal lattice. When potassium iodide dissolves in water, those attractions would be broken. Choice D talks about attractive forces between the potassium ions and the polar water molecules in the solution. When potassium iodide dissolves in water, those attractive forces would be formed. But since we're looking for an endothermic process that would relate to what this actually happened in terms of the dissolution of potassium iodide is classified as endothermic, the best answer for question 2 would be an endothermic process. So breaking attractive forces between potassium ions and iodide ions, that is the best explanation for the energy change that occurred during the dissolution of solid potassium iodide. So the correct answer to question 2 is choice C. Now let's take a look at question 3. In question 3, we are given an energy diagram or an energy profile. And it says, the diagram below represents the energy profile for the chemical reaction in which XY is produced, according to the equation above. Which of the following correctly classifies the energy change that occurs in this reaction and gives the correct value for the change in enthalpy for this reaction, or the delta H? We can see 4 choices, and we have to decide if this reaction is classified as endothermic or exothermic, and then we have to decide what is the actual value for the change in enthalpy for the reaction, which has units of kilojoules per mole of reaction. Now, these type of energy diagrams actually fall into 2 different topics in the AP Chemistry course and exam description. The first time such an energy diagram is mentioned is in the unit on kinetics, which is unit 5. And so in topic 5.6, which is reaction energy profile, one of the essential knowledge statements says that the energy profile gives the energy along the reaction coordinate, which typically proceeds from reactants through a transition state to products. And the energy difference between the reactants and the transition state is the activation energy for the forward reaction. Now, in this question 3 of this packet, we're not looking for the activation energy. Instead, we're looking for the change in enthalpy. So topic 6.2, energy diagrams, says a physical or chemical process can be described with an energy diagram that shows the endothermic or exothermic nature of that process. Another important topic in Unit 6 that relates to this question, question 3, is topic 6.6, enthalpy of reaction, which I will talk about in just a moment. Now, on this next slide, this is something I had presented in my video for topics 6.1 to 6.5. And this slide represents a compare and contrast between the energy diagram on the left, which is an endothermic process, and the energy diagram on the right, which is an exothermic process. So when we analyze an energy profile, if we notice that the potential energy of the products is higher than that of the reactants, then energy is absorbed as the reaction proceeds, and that reaction would be classified as endothermic. And the change in energy, or enthalpy, would be a positive number. But on the other hand, if we analyze an energy profile and we notice that the potential energy of the products is lower than that of the reactants, then energy is released as the reaction proceeds, and that reaction would be classified as exothermic. And the change in energy, or enthalpy, would be a negative number. So again, topic 6.6, Introduction to Enthalpy of Reaction, talks about that positive and negative sign. So it says, the enthalpy change of a reaction gives the amount of heat energy released for negative values, again, that would be an exothermic process, or absorbed for positive values, that would be for an endothermic process. So if you see that the change in enthalpy is positive, we have an endothermic reaction. And if you see that the change in enthalpy is negative, we have an exothermic reaction. Now, let's go ahead and remember that we're not looking for the activation energy, which would be the difference in energy between the reactants and that transition state. So we're not looking for the activation energy in this particular question. All right, we know that the potential energy of the products for this energy profile is lower than that of the reactants. So therefore, we can conclude that energy is released, and this is an exothermic reaction in which the sign of delta H is negative. So the correct answer is either B or D. Let's go ahead and eliminate choices A and C because it says endothermic. Now, the difference between the reactants and the products is going to be 50 kilojoules per mole of reaction, but that would be a negative number. So the correct answer is choice B, exothermic, and the delta H, or the change in enthalpy for this reaction, is negative 50 kilojoules per mole of reaction. So incidentally, even though this question did not ask for the activation energy, this is what that would look like. If I were to label the activation energy, would be 100 kilojoules per mole of reaction. But that's not what this question was talking about. So again, correct answer to question 3 is exothermic, negative 50 for the delta H, which is choice B. Now let's take a look at question 4. In question 4, it says, based on the information in the table above, which of the following experiments absorbs the greatest quantity of thermal energy? So we are given the specific heat, or the specific heat capacity for cadmium, which has the elemental symbol Cd, and for zinc, which has the elemental symbol Zn. So this question falls under topic 6.4, heat capacity and calorimetry. And so what's highlighted on this slide are some of the essential knowledge statements from topic 6.4. The amount of heat transferred between two bodies may be quantified by the heat transfer equation, which is Q equals M times C times delta T. And the transfer of a given amount of thermal energy will not produce the same temperature change in equal masses of matter with differing specific heat capacities. Now, the equation Q equals MC delta T can be found on your AP Chemistry Equations and Constants sheet in the section entitled Thermodynamics and Electrochemistry. So Q equals MC delta T is the equation in which Q represents the heat, which is normally measured in units of joules. M represents the mass, which is normally measured in units of grams. C is the specific heat capacity, or specific heat, and the units are normally joules per gram degrees Celsius, or sometimes joules per gram Kelvin. And the temperature would normally be either in degrees Celsius or Kelvin. So here we have the specific heat capacity for cadmium and zinc, and we have 4 choices, A, B, C, and D. Let's go ahead and start with choice A. So we know that the mass of the sample of cadmium is 4 grams. So that's going to be the M. The specific heat capacity for cadmium is 0.23 joules per gram degree Celsius. And then the temperature is changing from 20 to 90 degrees Celsius. That's a difference of 70 degrees Celsius. So when you pick up your calculator and you do 4 times 0.23 times 70, you get a value for the heat in units of joules, and that would be 64.4 for choice A. Now we're just going to repeat that process for choices B, C, and D until we can verify which one of these experiments will absorb the greatest quantity of heat or thermal energy. So on to choice B. We have the same mass, which is 4 grams. We have the same value for delta T, which is 70 degrees Celsius, but now our specific heat capacity for zinc is 0.39 joules per gram degree Celsius. Again, you pick up your calculator and you do 4 times 0.39 times 70, and the amount of joules this time is 109.2. So again, I'll just keep writing down all of the answers to these calculations. Moving on to question C, we have a different mass, so now it's 6 grams. This is cadmium, so it's going to be 0.23 for the specific heat capacity, and the delta T is from 20 to 60. That's a difference of 40 degrees Celsius. So when you pick up your calculator, it will be 6 times 0.23 times 40, and the amount of thermal energy in this case would be 55.2 joules. All right, finally, moving on to choice D. It's the same mass, 6 grams. It's the same delta T, which is 40 degrees Celsius, but now we use a specific heat capacity of 0.39 joules per gram degree Celsius. So you pick up your calculator, 6 times 0.39 times 40, and we get an answer of 93.6 joules. So now analyzing the results from choices A, B, C, and D, we can see that the correct answer to question 4, which of the following experiments absorbs the greatest quantity of thermal energy? The correct answer is choice B because it gives us the highest value for Q, or heat, or thermal energy. Now let's take a look at question 5. In question 5, it says a 100-gram sample of a metal was heated to 100 degrees Celsius and then quickly transferred to an insulated container holding 100 grams of water at 22 degrees Celsius. The temperature of the water rose to reach a final temperature of 35 degrees Celsius. Which of the following can be concluded? So just like question 4 in this packet, question 5 falls under topic 6.4, heat capacity and calorimetry. So for question 5, we need to consider that the amount of heat transferred between two bodies may be quantified by the heat transfer equation, which is Q equals mc delta T. Another thing to consider in question 5 is the first law of thermodynamics, which states that energy is conserved in chemical and physical processes. So what that means for this question is that the amount of heat or thermal energy that is lost by the metal will be equal to the amount of heat or thermal energy that is gained by the water in this experiment. And then something else to consider in question 5 is the fact that the metal and the water have different values for their specific heat capacity. So the transfer of a given amount of thermal energy will not produce the same temperature change in equal masses of matter with differing specific heat capacities. So what do we know so far about this experiment? Well, according to the first law of thermodynamics, the thermal energy that is lost by the metal should be equal to the thermal energy gained by the water. And with respect to the delta T, the temperature of the metal changes from 100 degrees Celsius to a final temperature of 35 degrees Celsius. That's a difference of 65 degrees Celsius for the metal. And the water, its temperature changes from 22 degrees Celsius to a final temperature of 35 degrees Celsius. That's a difference of 13 degrees Celsius. Now let's go ahead and start with choice A. In choice A, it says the metal temperature changed more than the water temperature did, and that's true. But then it goes on to conclude, therefore the metal lost more thermal energy than the water gained, and that's not true. Again, according to the first law of thermodynamics, the thermal energy that is lost by the metal should be equal to the thermal energy gained by the water. Let's go ahead and eliminate choice A. Now let's take a look at choice D, which says the final temperature, which is 35 degrees Celsius, is less than the average starting temperature of the metal and the water. So what they mean by that is 100 plus 22, which is 122. If you divide that by 2, you would get an average of 61. So what they're concluding in choice D is that the total energy of the metal and water decreased, and that's not true. And so the reason why that conclusion is incorrect is because the energy was simply transferred from the warmer object, which is the metal, to the cooler object, which is the water. So the total energy of the metal and the water did not decrease. The energy was simply transferred from the warmer metal to the cooler water. So we can eliminate choice D. Now let's focus on this idea of delta T and see how that relates to the specific heat capacity of these two substances. So what we have is 100 grams of metal. We have 100 grams of water. We have the same amount of heat that was lost by the metal and gained by the water. And that means that both Q, the heat, and M, the mass, are constant in this experiment. So what about the relationship between the other two variables, which are C, the specific heat capacity, and the delta T, the change in temperature? Well, they're going to be an inverse relationship in this equation. So as one gets bigger, the other gets smaller. And so if one substance experiences a larger value for the delta T, then that means that that substance should have a smaller value for its specific heat capacity. So because the metal experiences a larger delta T in this experiment, then it should have a smaller specific heat capacity. So the metal has a smaller specific heat capacity than the water because it experiences a larger delta T. So in choice C, it says the metal temperature changed more than the water temperature did, which is true, but it goes on to conclude, therefore the heat capacity of the metal must be greater than the heat capacity of the water, and that part is not true. So we can eliminate choice C. So as you can see, the correct answer to question 5 is choice B. The metal temperature changed more than the water temperature did, which is true, but the metal, according to the first law of thermodynamics, the metal lost the same amount of thermal energy as the water gained. So again, the correct answer to question 5 is choice B. Now let's take a look at question 6. In question 6, it says a student heated samples of methanol, which is CH3OH, and water. Data from the experiment is shown in the table above. Based on the information in the table, which of the following correctly compares the change in the average kinetic energy of the molecules in the samples and provides the correct justification? Now, in the previous question, question 5, it turned out that the specific heat capacity of the metal was different than the specific heat capacity of the water. Here, in this table, we can see that the specific heat capacity of liquid methanol, CH3OH, is different than the specific heat capacity of liquid water. So we might be tempted to focus on this difference in specific heat capacity as we are analyzing the information in this table. But pay close attention, we're not talking about thermal energy, which is heat. We're talking about the change in the average kinetic energy of the molecules in the samples. So I'm going to go ahead and present on this next slide information that actually comes from Unit 3. Unit 3 is entitled Intermolecular Forces, and one of the topics in Unit 3 is topic 3.5, which is kinetic molecular theory. So what I'm highlighting on this slide from topic 3.5 is the following. The Kelvin temperature of a sample of matter is proportional to the average kinetic energy of the particles in the sample. So all we need to do to answer question 6 correctly is focus on the temperature, not the heat, not the thermal energy, but rather the average kinetic energy of the molecules in the samples. So because all we have to focus on is the temperature, take a look at what happened during this experiment. The temperature of liquid methanol changes from 25 degrees Celsius to 55 degrees Celsius. And even though the water does have a different specific heat capacity compared to methanol, its temperature, the water's temperature, also changes from 25 degrees Celsius to 55 degrees Celsius. And again, because we're not focusing on thermal energy, but rather the average kinetic energy of the molecules in the samples, the answer is going to be either choice C or D, which is the same. So the absolute temperature is a measure of the average kinetic energy of the particles of a substance. In this experiment, the temperature change is the same for these two samples. Therefore, we can conclude that the change in the average kinetic energy of the molecules in these two samples should be the same. Now, the reason why the correct answer is not choice C is because of the justification. It says that each sample has the same mass. It's not about the mass, it's about the temperature. So the correct answer to question 6 is choice D. The change in the average kinetic energy of the molecules is the same for both samples, but the reason why, the justification, is the fact that the initial and final temperatures are the same. Now let's take a look at question 7. In question 7, it says, a student performed an experiment to determine the value of the enthalpy change, delta H, for the reaction between solid magnesium oxide, or MgO, and aqueous hydrochloric acid, HCl, as represented by the equation shown above. The student combined a sample of solid magnesium oxide with an excess amount of aqueous hydrochloric acid in a coffee cup calorimeter. Data from the experiment are shown in the table below. Which of the following is the enthalpy change of the reaction represented above? So because this is a calorimetry experiment, this falls under topic 6.4, heat capacity and calorimetry. So we will need to use the equation Q equals mc delta T. We will also need to use the specific heat capacity, which they will give us for the reaction mixture. And it's important to note that chemical systems change their energy through 3 main processes: heating and cooling, such as transferring a hot piece of metal to room temperature water, which we saw earlier in this packet; phase transitions, such as melting, freezing, evaporation, condensation; and chemical reactions. So here in question 7, we have an example of a chemical reaction, and there is a calorimetry experiment using a coffee cup calorimeter. So let's go ahead and use Q equals mc delta T to calculate the amount of heat associated with the chemical reaction that occurred in this experiment. So the M represents the mass. The total mass of the reaction mixture is 100.00 grams. The C is the specific heat capacity, and we are told that the specific heat capacity of the reaction mixture is 4.2 joules per gram degree Celsius. And the change in temperature is going to be from 20 degrees Celsius to 55.7 degrees Celsius. So that's a delta T, or a difference in temperature, of 35.7 degrees Celsius. So if you pick up your calculator and you do 100 times 4.2 times 35.7, you get a value of 14,994, and that would be units of joules. Now that's close enough to round up to 15,000 joules, and when we go from units of joules to units of kilojoules, we divide by 1,000. So there's 1 kilojoule for every 1,000 joules. So now I have an answer of 15 kilojoules. You might think that the correct answer to question 7 is either choice B or C, because we just got a value of 15 kilojoules by using Q equals mc delta T. But focus on the units in all 4 of these answer choices. It's not just kilojoules, it's kilojoules per mole of reaction. So what exactly is mole of reaction? Now in my video for topics 6.6 to 6.9, in topic 6.6 it says the enthalpy change of a reaction gives the amount of heat energy released for negative values, or exothermic processes, or absorbed for positive values, or endothermic processes, by a chemical reaction at constant pressure. So in that video, I talked about the concept of mole of reaction. So mole of reaction is a unit that is defined in terms of the specific set of coefficients for a particular chemical equation. Let's go back and take a look at the chemical equation in question 7. So there's 1 mole of magnesium oxide reacting with 2 moles of hydrochloric acid. But they said in this experiment that the student combined a sample of magnesium oxide with an excess amount of hydrochloric acid. that means all we have to do is focus on the limiting reactant, not the excess reactant, but the limiting reactant. So the limiting reactant is magnesium oxide. And we can see that there's a coefficient of 1 for the magnesium oxide in this balanced chemical equation. So for every 1 mole of solid magnesium oxide that is consumed in this reaction, that would correspond to 1 mole of reaction. Now we do have 15 kilojoules, but we need to get the moles. So we have to convert the grams of magnesium oxide that was used in this experiment, which is 4.03 grams, into moles. And the molar mass of magnesium oxide is 40.3. So it's 4.03 divided by 40.3, and that tells us that we have 0.10 mole of magnesium oxide, or 0.10 mole of reaction in this experiment. So 15 kilojoules of heat is associated with 0.10 mole of reaction, and that means that the correct answer is going to be 150 kilojoules per mole of reaction. So 15 divided by 0.1 is 150. Let me go ahead and eliminate choices B and C. Now that we know that the correct answer is either A or D, 150 kilojoules per mole of reaction, we have to consider what happened to the temperature as this reaction proceeded. So the temperature of the reaction mixture increases as the reaction proceeds. Remember that when the temperature increases during a chemical reaction, that's going to be an exothermic process. So this chemical reaction releases energy. The reaction is exothermic, and therefore the sign of delta H for this reaction should be negative. So the correct answer to question 7 is choice A. The enthalpy change of the reaction is negative 150 kilojoules per mole of reaction. Now let's take a look at question 8. In question 8, it says, a student performs a calorimetry experiment to determine the change in enthalpy for the dissolution of solid lithium chloride, LiCl, in water. Data from the experiment is shown in the table above. Which of the following is the most likely value for the final temperature of the solution in trial 2? So first, let's consider the information that we have for trial 1. In trial 1, the student used 10 grams of solid lithium chloride, and it was dissolved in 90 grams of water. The initial temperature of the water was 20 degrees Celsius before the lithium chloride was added, and the final temperature of the solution is 40.8 degrees Celsius. So we can see that the dissolution of solid lithium chloride in water is an exothermic process. Because the temperature increased, that means that heat was released, and so the dissolution of lithium chloride in water is an exothermic process. Now when we use Q equals mc delta T to calculate the amount of heat that was released in trial 1, remember that the M represents the mass, but students might be confused about which mass they should use. If you're doing a calculation for the enthalpy of solution, we always add the combined mass of both the solute, in this case lithium chloride, and the solvent, in this case the water. Those are added together. So the total mass of the solution is 10 plus 90, or 100 grams. So I've got my Q equals mc delta T. I have 100 grams of solution in this experiment for trial 1. We were not given the value for the specific heat capacity of the solution, so I'll skip that part for now and just put a question mark in that spot. And then the delta T would be the change in temperature. So it's going to be 40.8 degrees Celsius, the final temperature, minus 20 degrees Celsius, the initial temperature. That's a difference of 20.8 degrees Celsius. Now I can't pick up my calculator and do 100 times a number I don't know, and then times 20.8, but let's go ahead and process the information that we're given for trial 2 and compare that to the information we're given for trial 1. So for trial 1, we have 100 grams of solution, and we have a change in temperature of 20.8 degrees Celsius. Now, in trial 2, the student also used 10 grams of solid lithium chloride, but the difference is that they used a larger mass of water. The total mass of water was 190 grams in trial 2. What's important, though, is that lithium chloride, that mass, did not change. And it's the lithium chloride that's actually producing the energy change in this experiment. So if the same amount of lithium chloride was used in trial 2 as in trial 1, then that means the amount of heat that is released is going to be the same. So the amount of heat, or Q, that is produced in trial 2 should be the same as the amount of heat produced in trial 1. And that's because the mass of lithium chloride is the same in each of these trials. So I would have Q equals MC delta T, but of course my mass is different. The total mass of the solution in trial 2 is not 100 grams, it's not 10 plus 90, it's actually 10 plus 190, or 200 grams of solution. Again, we don't know the specific heat capacity of the solution, and we also don't know at this point what the delta T, or the change in temperature, is. Now, because these solutions are mostly made of water, it is a reasonable assumption that the specific heat capacity of the solution in trial 1 and trial 2 are going to be the same, or very approximately the same, for the purpose of answering this question. So because we can assume that the specific heat capacity of the solution, which is mostly water, is the same in each trial, I'm just going to put a number in that spot. And I put 4.2 because that's very close to the specific heat capacity of water. So trial 1, I have 100 times 4.2 times 20.8, and that's my value of Q in joules. For trial 2, I have 200 times 4.2 times a delta T that I haven't determined yet. But since the amount of heat, or Q, is the same, then we can look at this inverse relationship between mass and delta T in this equation. So because the mass of the solution in trial 2 is twice as much as the mass of the solution in trial 1, then to keep these values of Q, or heat, the same, then I can say that the delta T in trial 2 should be half as much as the value of delta T in trial 1. So what's half of 20.8? Well, half of 20.8 would be 10.4. So comparing trial 1 and trial 2, the amount of heat produced in trial 2 should be the same as the amount of heat produced in trial 1. But since the mass of solution in trial 2 was twice as much, that means that the value of delta T should be half as much compared to trial 1. So the correct answer to question 8 can now be determined. If the value of delta T in trial 2 should be equal to 10.4 degrees Celsius, then 20 plus 10.4 will give us the final temperature of the solution. So 20 plus 10.4 is 30.4 degrees Celsius. So the correct answer to question 8 is choice B. Now let's take a look at question 9. In question 9, it says a student conducted an experiment to determine the change in enthalpy, or the delta H, for the reaction between aqueous hydrochloric acid, HCl, and aqueous sodium hydroxide, NaOH. The student ran 2 trials using the volumes of hydrochloric acid and sodium hydroxide indicated in the table above, and determined the amount of heat released. Which of the following best explains the relationship between X and Y? So let's start by considering the information in the table for trial 1. So in trial 1, we have 50 milliliters of 0.10 molar hydrochloric acid, and then we have 50 milliliters of 0.10 molar sodium hydroxide. Now, when we are given volume and molarity, we can calculate the number of moles. So volume in liters times the molarity will give us the number of moles. So for trial 1, it's going to be 50 milliliters. First, I'm going to convert from milliliters to liters. And there's 1 liter for every 1,000 milliliters, so 50 divided by 1,000. And then the molarity is 0.10 moles of HCl per liter. So if I do that math, that would be 50 divided by 1,000 times 0.1. And when I do that math, I get the number of moles of HCl, 0.0050 moles of HCl. But if you notice, it's the same volume for sodium hydroxide and it's the same concentration. So 50 divided by 1,000 times 0.1, that will give me the same number of moles of sodium hydroxide, 0.0050 moles. So that's the information for number of moles of each reactant for trial 1. Now, if you notice, they did double the volume of hydrochloric acid going from trial 1 to trial 2, but they did not change the volume of the sodium hydroxide. So when we look at the calculations for trial 2, the number of moles of HCl will be twice as much. So it's going to be 100 milliliters, again converting from milliliters to liters, so times 1 liter over 1,000 milliliters, and then times the molarity, which is still 0.10 moles per liter for HCl. So 100 divided by 1,000 times 0.1 gives me 0.010 moles of HCl, but the number of moles of sodium hydroxide in trial 2 is the same as it is in trial 1. Now you might think, how does this affect the amount of heat released? But this has to do with something you learned back in Unit 4. So in topic 4.5, which is stoichiometry, we need to consider not only the mole ratios, but also this idea of a limiting reactant, as well as the theoretical yield. So the definition of the limiting reactant in a chemical reaction is the reactant that is completely consumed when the chemical reaction is completed, and the limiting reactant determines the maximum amount of product that can be produced, which is known as the theoretical yield. Now, it says the amount of heat released. You can think of heat as a product of this particular chemical reaction. And the amount of heat released is going to be the same in both of these trials. And the reason why is because sodium hydroxide turns out to be the limiting reactant both in trial 1 and in trial 2. Of course, in trial 1, there's not really a limiting reactant. There's simply the same amount of moles of each, and that matches the 1-to-1 mole ratio in the balanced chemical equation. But when we go from trial 1 to trial 2, because they only doubled the amount of hydrochloric acid, but they did not change the amount of sodium hydroxide, then that sodium hydroxide is going to be the limiting reactant, which limits how much heat is produced. So the amount of heat released in trial 2 should be the same as the amount of heat released in trial 1, again, because sodium hydroxide is the limiting reactant. So now the correct answer to question 9 is choice B. It says, which of the following best explains the relationship between X and Y, or the amount of heat released? And the answer is choice B. Those two values are the same because the number of moles of acid and base reacting with each other is the same in both trials. Again, it has to do with the fact that sodium hydroxide is the limiting reactant in trial 2. Now let's take a look at question 10. In question 10, we are given a data table, and in the data table, it refers to information for the element gallium, which has the symbol Ga. We are given the specific heat capacity of liquid gallium. We are given the heat of fusion, which has to do with the amount of heat required to melt gallium. And then we're also given the melting point of gallium. So in question 10, it says, a sample of solid gallium at 29.8 degrees Celsius is added to 100 grams of liquid gallium at 83.9 degrees Celsius. The mixture is stirred gently until the temperature is 29.8 degrees Celsius. All of the remaining solid gallium is quickly removed. Based on the information in the table above, the mass of solid gallium that melted in this experiment is closest to, and then we have 4 numerical choices. So this question falls under topic 6.5, energy of phase changes. So there was definitely a phase change that occurred in this experiment in that a sample of solid gallium melted when it was added to a sample of liquid gallium that was at a higher temperature. So the energy was transferred, and that caused the substance to melt. I think it might be easier if I can show you a simple diagram for what occurred during this experiment. So here I have a beaker that contains 100 grams of liquid gallium, and the temperature is 83.9 degrees Celsius. Now, to this sample of liquid gallium, a sample of solid gallium at a temperature of 29.8 degrees Celsius was added to that beaker. And so as a result of that, some of the heat was transferred from the hotter object, which is the liquid gallium, to the cooler object, which was the solid gallium. So the mixture is stirred gently until the final temperature is 29.8 degrees Celsius. Now all of the remaining solid gallium is quickly removed, and now we have a final temperature of 29.8 degrees Celsius. So that liquid gallium cooled off, which means it lost some heat, but the heat that was lost by the liquid gallium in this experiment is also equal to the heat gained by the solid gallium as it melted. So we're going to do a Q equals MC delta T calculation to figure out how much heat was lost by the liquid gallium, which will also be the amount of heat gained when the solid gallium melted. So the temperature of that 100 gram sample of liquid gallium decreased from 83.9 degrees Celsius to a final temperature of 29.8 degrees Celsius. Let's go ahead and set up a Q equals MC delta T for the liquid gallium. The specific heat capacity is 0.37 joules per gram degree Celsius for liquid gallium. So here is the heat lost by the liquid gallium equals Q, which is MC delta T. So M is the mass of the liquid gallium, which is 100 grams. C is the specific heat capacity of the liquid gallium, which is 0.37 joules per gram degree Celsius. And because the initial temperature was 83.9 degrees Celsius and the final temperature is 29.8 degrees Celsius, we have our delta T. So I will pick up my calculator and do 100 times 0.37 and then times the quantity which represents the delta T. That's a difference of 83.9 minus 29.8. And when I do that math, I get the amount of heat that was lost by the liquid gallium in this experiment, and it works out to be 2001.7 joules. But the heat that was lost by the liquid gallium was also the heat gained by the sample of solid gallium that melted. So the heat gained by the sample of gallium solid that melted is 2001.7. Now, in the data table, it says the heat of fusion is 80.0 or 80 joules per gram. So what that means is that it takes 80 joules to melt 1 gram of gallium. So if there's 2001.7 joules of heat transferred to the solid gallium, I'm going to divide by 80 because there's 1 gram of solid gallium for every 80 joules required to melt that solid. And so 2001.7 divided by 80, that will give me the number of grams of solid gallium that melted in this experiment. And that's what we're trying to find in question 10. So 2001.7 divided by 80 gives me 25 grams. So that is my answer to question 10. The heat that was lost by the liquid gallium, which cooled off in this experiment, is equal to the heat that was gained by the sample of solid gallium that melted. So the correct answer to question 10 is choice C, 25 grams. Now let's take a look at question 11. In question 11, we are given a diagram which is the heating curve for methane, CH4. And it says the energy required to vaporize a 120 gram sample of liquid methane at its boiling point is closest to, and then we have 4 numerical choices. So this question, because it has to do with phase changes, falls under topic 6.5, energy of phase changes. So the energy of the system increases. So it's an endothermic process, either to melt, to go from a solid to a liquid, or to vaporize or evaporate, going from a liquid to a gas. So we're focusing on the liquid to gas transition. And that would be located where it says delta H of vaporization, or VAP. So from the information in the diagram, we can see it takes 8.2 kilojoules of heat to vaporize 1 mole of liquid methane at its boiling point. Now, because the units are kilojoules per mole, but we are given a 120 gram sample of liquid methane, we're going to have to convert from grams to moles. So let's use the information in the periodic table to calculate the molar mass of methane. So carbon has a mass of 12.01. Hydrogen has a mass of 1.008. We have 1 carbon and 4 hydrogens in the formula for methane. That's a total mass, or a molar mass, of 16.042 grams per mole. So let's start with 120 grams of methane. Then I'll use the molar mass to convert from grams to moles. So 1 mole of methane for every 16.042 grams. Now let's go from moles to kilojoules. Again, for vaporization, from the diagram, it would be 8.2 kilojoules of heat for every 1 mole of methane. So I'll pick up my calculator and do 120 divided by 16.042 times 8.2. And that quantity, which is 61.3, represents the amount of heat in kilojoules that is required to vaporize a 120 gram sample of liquid methane. Now, of the 4 choices, choice C is closest. It says 62 kilojoules. Even though the answer that I just got on my calculator is 61.3, that is closer than any of the other choices. Now, if I just rounded off my molar mass to, let's say, 16 instead of 16.042, which is a little more precise, 120 divided by 16 times 8.2, I would get a value of 61.5. So the correct answer to question 11 is choice C, 62 kilojoules. So question 11 is the last question in this packet. I hope that you found all of these answers and explanations helpful. Thanks for watching.